All right, so let's try the other direction, which is I want to resolve components given some angle and length information, right? So if you walk away from the origin at an angle of 30 degrees, right, really with the x-axis for 5 units, whatever that means, what's the vector describing your movement?
4, 3.
Nice. Wait. Okay. Good thought, though, Alvin. Do you guys see what Alvin noticed?
3, 4, 5 triangle.
Yeah, he sort of noticed a 3, 4, 5 triangle and thought I would have built that in.
And I visualized it.
Yeah, that's close to a 30-degree angle, but not quite. All right, so what's the vector I'm making here? What do I know about this vector?
It goes up from the origin at a 30-degree angle and goes up.
Okay, so it starts at the origin and goes somewhere, right? How far is it from the origin to the somewhere?
5 units.
5 units.
5 units. Okay, and then what about this angle was known?
30 degrees.
That's 30 degrees. Okay, now what?
Triangle and
Yeah, okay, so now I need to bust out my 30, 60, 90 triangle, right? So I'm looking at this thing and I'm thinking, okay, 30, 90, 60. What do I know about the sides of this thing?
The hypotenuse is 5.
Yeah, I know the hypotenuse is 5 in that picture. What do I know about the standard one? The hypotenuse is 2, opposite of 30 is 1, and this is square root of 3. Okay, so what did I do to get from the standard triangle to the triangle I'm dealing with?
Multiplied it by 2.5.
Yeah, I think I multiplied it by 5 over 2. Okay, see that? That's the kind of similar triangles approach. So what are the components of the vector I'm looking for? So there's this picture, right? Why did I even start doing this triangle?
you find the x and y.
Oh yeah, I need to define the x and the y, right? So that's like this distance and this distance, yeah? Okay, so what are those now?
5 root 3 and 5.
I think this one's 5 over 2, and this one is
5 over 2 times
5 over 2 times root 3, or 5 root 3 over 2.
Yeah,
Cool. So what's my vector answer?
5 over 2 root 3 comma
5 root 3 over 2, comma 5 over 2. Okay, what's another way I could have thought of that? So I went and found a similar triangle, right? But how else could you have done this? Yeah, you could have used a formula, right? Which formula do you want?
inverse.
Ah. Yeah, the one that's someplace on the same page is an inverse tangent.
X equals r cosine theta.
Good. This here is r cosine of theta. Oh. Where r is what?
Out of 5.
Yeah, that 5, not theta. That 5 is r, and the 30 is theta, right? How about the other one?
Y equals r sine.
Yeah, that's a y thing, so you might think r sine theta there. You guys with me on this? Okay, cool. So is there any difference really between converting from degree and distance information to vectors and polar? Like, what's the subtlety? Why didn't I just do this the day we did polar?
Shows multiple approaches.
So the reason I didn't do this the day we did polar is that these symbols wouldn't have done anything then. But that's really it. You guys see that? So don't think there's new tools, right? This is all the same stuff. This all goes back to SOHCAHTOA, right?